Section: Introduction. In this section, we introduce the linear representation hypothesis, which suggests that models express high-level concepts as linear directions in activation space. This idea has inspired various techniques to modify the behavior of large language models, LLMs, through linear changes in their activation streams. Two effective techniques are directional ablation and activation addition. We explore a unified approach to these methods, which we refer to as affine concept editing, and we apply this to a recurrent neural network from the RWKV-V5 family. We highlight a key ambiguity in the existing literature on the linear representation hypothesis. The term linear representation can refer to either a linear function, which lacks a constant term, or an affine function, which includes a constant term that may be zero. We demonstrate that this distinction is significant. Methods that assume linear encoding can lead to nonsensical outputs, while our generalized affine approach successfully guides the model. Next, we discuss linear decomposition. Given an activation vector and a non-zero vector, we can break down the activation vector into components that are parallel and perpendicular to the given vector. The parallel component can be expressed as a multiple of the vector, and we interpret this multiple as the extent to which a certain behavior is represented in the activation vector. This leads to potential steering interventions, such as adjusting this multiple by a fixed amount or setting it to zero to remove the behavior. However, we argue that this linear framework is too limited. It incorrectly assumes that the zero vector represents a meaningful absence of behavior. In reality, most behaviors in a network are not absent, and typical activations are often far from zero. We extend the framework by incorporating a reference point that represents a standard level of behavior. This allows us to decompose the activation vector in a way that accounts for both the behavior vector and the reference point. In this new decomposition, we express the activation vector in terms of the reference point and the behavior vector. The reference point determines the zero point for our multiple, which is now an affine function that includes both a linear term and a constant term. This leads to new steering methods, where we can zero out or set the multiple to a new value based on this affine representation. By defining a specific value for the multiple based on the reference point, we can achieve a more comprehensive and effective steering approach. We show that with appropriate choices for the reference point and the behavior vector, this affine method provides better control over model behavior and prevents nonsensical outputs when steering. Section Summary. In this section, we introduce the concept of affine concept editing, which generalizes existing techniques for modifying large language models by addressing the ambiguity between linear and affine representations in activation space. We demonstrate that our affine approach provides more reliable control over model behavior and prevents nonsensical outputs, highlighting the importance of a reference point in the decomposition of activation vectors. Section: Standardized steering. In this section, we define standardized steering as the consistent control of behavior based on a specific steering parameter. We say a steering technique is standardized if fixing this parameter leads to a consistent level of behavior, regardless of the input prompt. If the behavior varies with different prompts, the technique is not standardized. For a steering method to be considered standardized, setting the parameter to 1 should produce the desired behavior, while setting it to 0 should result in no behavior at all. We provide examples to illustrate standardized versus non-standardized steering. When we talk about refusal, we define the behavior as refusal and the absence of it as non-refusal. We believe this distinction is clear, but we could analyze it differently if we chose. Whether standardization is beneficial depends on the application. If we aim to influence a model's behavior without complete control, non-standardized methods might be better. However, if we want full control, especially in cases of refusal, standardized techniques are necessary. We demonstrate that contrastive activation addition, CAA, is not a standardized method for steering refusal, while directional ablation does not generalize well across models. We also show that our proposed method, affine concept editing, ACE, addresses both issues, being more standardized than CAA and more general than directional ablation. CAA modifies a model's activations by adding a weighted difference between positive and negative examples. However, a key limitation of CAA is that it does not account for how much of the target behavior is already present in the model, leading to non-standardized outcomes. Directional ablation alters model activations by projecting them in a way that is more standardized than CAA, but it still cannot fully control the behavior. While it can remove certain information, it may lead to nonsensical outputs in some models. We propose ACE as a combination of CAA and a refined directional ablation, which provides a more complete approach. We ensure that the expected values of the steered activations align with known behaviors. In ACE, the parameter we use has a clearer meaning, as it determines how much the steering vector influences the resulting activations. In this way, ACE allows us to set the expected expression of the target behavior to a specific value, enhancing both standardization and control. Section Summary. In this section, we define standardized steering as the consistent control of behavior based on a steering parameter, where setting the parameter to 1 induces the desired behavior and 0 induces no behavior. We introduce Affine concept editing, ACE, as a method that combines the strengths of contrastive activation addition, CAA, and directional ablation, achieving both standardization and preventing nonsensical outputs across different models. Section Results. In this section, we conduct 2 experiments with ACE to assess its impact on steering refusal. The first experiment, involving Llama 3, shows that ACE achieves better standardization compared to CAA. The second experiment, using Hermes Eagle RWKVV5, reveals that ACE generates coherent text, while directional ablation leads to nonsensical outputs. Our findings on Llama 3 indicate effective standardization in refusal steering, as illustrated in the tables and figures, which display the probability of refusal across various steering parameters for both ACE and CAA-only steering. We utilized Llama 370B Instruct as a scoring model to determine if the prompt was refused for a given response, with more details available in the appendix. While we found that directional ablation effectively controlled refusal in several models, applying this method to Hermes Eagle RWKVV5 resulted in nonsensical outputs. Upon reviewing the activation vectors, we noted that directional ablation was too strong of an intervention for this model, unlike in Llama 2. By integrating corrected directional ablation with activation addition, we achieve improved standardization. Although ACE's standardization effect is not flawless, we observe that parameters slightly below 0 and slightly above 1 yield the best results. This is evident in the probability of refusal curves for both prompt types, which converge around these parameter values. For Llama 3.8b at layer 15, we find that ACE is nearly perfectly standardized at -0.5 and +1.5. While ACE demonstrates a superior standardizing effect compared to CAA alone, our results indicate that this effect is not entirely perfect. This may suggest that the steering vectors we derived have some flaws or that directional ablation does not completely eliminate information. Initial experiments with more advanced erasure techniques, like LEAS, did not enhance standardization and often worsened the results. Future research should explore whether it is possible to completely erase concepts like refusal in a linear manner or if nonlinear methods are necessary. Additionally, further investigation is needed to adapt these techniques for a broader range of behaviors.